So I tried to put together some material that I thought you'd be interested in, and there's some interesting stuff that's not really applicable at the beginning, but over the last year or so I've been doing a lot of historical research on radios, so I tried to pull some of those things in and share that with you, and actually show you how it links into some of the work that I actually do today, because believe it or not, even though radio's been around now for over 100 years, we still use a lot of the same principles that they used back in the early days. So to start that, I thought what I'd do is I would share some of the history behind transmitters. And so what we've got here on the top left is an old spark gap transmitter. And it was kind of a rotary wheel thing where you can kind of see this thing in the background with the little spikes on it. It would spin around. It had a really high voltage on it, maybe up to 150 kilovolts. And that would periodically discharge into some of the electrodes up there, and that created the RF energy that they would run to some kind of resonator to create the RF. But one of the interesting things I found in digging this up is that this required a capacitor to help build up the charge. And this is a picture, it's a little bit hard to see, but of a capacitor that they had built by stringing these plates from the ceiling. And down in the bottom you can see a guy, he's about maybe 10% of the total height. So these are huge multi-plate capacitors that took a whole building to put in. And I thought that was kind of interesting. Not very efficient, but this is one of the first transmitters that they had. One of the next things they did was they realized, hey, we can build generators that create RF. And so this is one of the early, I guess it's called an Alexanderson alternator. This one happens to be in Sweden, and I think it still works. But does anybody care to guess what the operating frequency of that alternator is? No guesses? Well, I give you a hint. If it was audio, you could hear it. It was so low. It was 17.2 kilohertz. So it was really low frequency. Then I guess in the 30s they started developing tubes, and let's see. Yep, there we go. So the one with the old man up there holding on something that kind of looks like a pogo stick, that's a 100 kilowatt PA final tube. And if you Google that if you look at it on the internet, you can find a bunch of pictures like this, and it seems like everybody's always holding them like that because the electrodes on the side, I guess, kind of look like handlebars or something. The one down on the bottom is an old ham transmitter. I actually have one of these. That's not a picture of mine, but it's an old tube type built in the 1950s. It's actually a pretty cool old set. But you can kind of see technology's changed a lot over the last 100 years, from the early 1900s up through 1950. The last time I was here, Jeff tells me or Dr. E tells me, was 15 years ago. And one of the things that I talked about then were the chips over there on the far right. Those we called, interestingly enough, transmit DACs or TX DACs. Basically, they're RF sampling DACs, basically. So back in 2000, 2005, we were able to synthesize and transmit frequencies up to about 150, 200 megahertz. So that was high tech just 15 years ago. So things have kind of changed a lot back then. The board on the bottom there is an eval board that we had built for our RF DACs. But you can kind of see what's happened from, let's say, 1905 to 2005. Big differences over the years. On the receiver side, you see some of the same sort of things. This is kind of a setup very similar to what was on the Titanic. It's got parts of the transmitter in there, but the main receiver is this kind of thing right here, and I'll talk more about that in a minute. Then maybe some of you have seen crystal radios. I've got another picture in a minute, but one of the interesting things about the early receiver technology is that they're all passive. They don't have any sense of gain. So all of the energy that you collected on the antenna, it ultimately came down and was somewhere rectified, and that went to a little speaker, and you can see the little speaker right there. You kind of had to hold onto your ear like that. That was all the energy you had to drive that little speaker was what you capture with the antenna. So if you wanted a higher volume, you either needed a bigger antenna or you needed a bigger transmitter. There was no way to turn up the gain on the receive end. So some interesting things about that, and I'll talk about both of those in a minute as well. 1940 kind of vintage receiver technology. Maybe some of your grandparents still had some of these. My grandfather had a bunch of these. He gave me one, and I lost it, unfortunately, over the years. But those were pretty good. And then when I was here in 2000 something or other, 2003, this was one of the things that I'd spent a lot of time working on. And this was a multi-carrier receiver. And we were able to do direct RF sampling up to about 65 megahertz or so with this. Then we had a DVC board that we took the wideband signal and we decimated the rate down to whatever our channel bandwidth was. Then we had a serial interface that went over to our DSP board. And then you can kind of read the footnotes on the demo there. We could actually go between AM modulation, FM, upper sideband, lower sideband, and just kind of cycle around. We actually had a transmitter very similar to this as well. So we had a lot of neat demos where we could send multi-carrier RF through the medium. It's pretty cool stuff. But again, maybe 100 megahertz was all we could get out of this in 2005. So a lot's changed since then, and again, we'll talk more about that in a few minutes. I wanted to back up to the radio that was in the Titanic. One of the things that Marconi really liked to use, and Marconi was the guy who had staffed all these ships that were in the ocean with their transmitter and receiver equipment. His favorite receiver was called a magnetic detector, and that's what this shows here. It had basically an endless loop of steel wire that would rotate between these circular things, and somebody's taken it off on this one. You can kind of see what it looks like up on that one. And it would either have a wind up or hand crank or something that would cause the magnetic wire to loop. The permanent horseshoe magnets would basically erase the noise that was on the steel wire, but then the RF signal would come in on the antenna, and there was some kind of LC resonant circuit across there, but that RF energy then would interfere with the permanent magnet and basically put the modulation on the steel wire. And then the pickup for that right here would detect those variations in the magnetic flux on the steel wire, and that was your audio. So again, no gain. But this was Marconi's favorite receiver up until Titanic. Didn't work very well, but that's the technology that he had to use at the time. The other thing, and some of you may have seen these, you can still buy these out on Amazon, and when I was putting this together, that's where I got this color picture down in the bottom. Mostly they're just kind of toy things, but again, very simple kind of receiver. You had your antenna that came down to kind of a parallel resonant LC circuitry, and then that went to a detector diode, and they didn't have the semiconductor diodes we have today. Marconi and I guess Alexander Fleming invented the vacuum tube valve is what they called it, which eventually became a detector. Marconi didn't like that. He preferred his Maggie, so he didn't use that. But what they used were these little mineral detectors. So they used little rocks of galenium, iron pyrite, or you can see the others there, or carborundum. One of the interesting things about this was that the silicon carbide crystals, a lot of the reports would say that operators would actually see little bursts of light coming off of them. And if any of you guys do PAs or LEDs, you'll recognize that silicon carbide is one of the choices that you can use for substrates on LEDs as well as amplifiers. So serendipitously, they also discovered LEDs back 100 years ago or so. So to kind of make things a little more personal, I'll tell you a little bit about some of the things that got me interested in radio. So 1968, that tells you how old I was. My parents gave me one of these for my birthday, and mine's long since gone. This is one that I got off the web. And they got it from a store called Radio Shack, which I don't think is around anymore. Not too many of them anyway. But they gave me one of these, and this was great. My birthday is around Thanksgiving, so all of Thanksgiving and Christmas of 1968, I took this everywhere with me and played with it. And it's got a couple connectors on there. You can see on the right there's a place for the earphone, which is not connected. There's two antenna connectors. There's a short wire you could use and a long wire. that you can use, and you connect that up like so. And I sort of intuitively understood what an antenna was. You're kind of collecting the energy in the air. But the one that I had the most trouble with was ground. As an 8-year-old, I kind of had a hard time understanding what the concept of ground was. So this was one of my first engineering projects, is to try and understand what ground was. And fortunately, it came with a pretty good set of instructions. It said, you know, take that ground wire and connect it to your telephone. And I think if you got one of these today, you'd pull out your phone and say, where do I connect it? How does it work? Is it like the power supply or something? Well, no, you connected it up to one of these, which I doubt any of you guys have seen. But it turns out that the finger stop on this, you put your finger in here and you twirl it around. Have any of you actually ever used one of these phones? Oh, wow, there's a couple hands. It turns out this metal stop right here that kept your finger from going around in endless circles, that made a really good ground. So that's how I solved my ground problem. I guess you could also tie it to the cold water pipe at your house or something like that. But anyway, I spent all of Thanksgiving and Christmas of 1968, everywhere I went, taking this with me, connecting it to everybody's telephone. But that was really one of my first engineering challenges, is to figure out what ground was. And so I thought I'd kind of pose this rhetorical question to you and say, you know, what does an engineer do, right? You guys are all studying to be engineers of some kind. And my guess is right now you spend a lot of time studying, right? Is there anybody who doesn't study? No hands, right? You also spend a lot of time in the lab, but mostly you solve problems, right? And that's kind of what I was doing as an 8-year-old, was trying to figure out how to solve my ground problem. But engineers, a lot of times, you solve problems you didn't really know existed, and you use techniques that you don't necessarily understand. But that's why you're in school, and eventually you'll go off and get a job somewhere. You know, you'll solve these kind of problems. Hopefully when you're done, you do understand what the techniques are that you're using, and you're probably an expert in the problem at that point. And that's really kind of why we become engineers, is to learn new things and to solve problems. So some of the specific challenges that you know, I see as a radio engineer, I all the time get customers asking me for more power out of a transmitter, or they want more linearity or better linearity. They may want wider bandwidth, or they may want higher operating frequencies. And so this is one of the fundamental problems that I've solved and my cohorts over the years have solved. If we go back to our early examples where I was showing you the old pictures, you know, I talked about that transmitter at 17.2 kilohertz. Back around the 1900s, 1900, 1910, kind of in that range of time, they pretty much thought that frequencies above 200 kilohertz were useless. There was just no use for them. You couldn't do anything with them. And then by World War II, that had kind of moved up to 10 megahertz. And so there were some interesting things going on there in terms of, I guess, intelligence or counterintelligence, where they were trying to listen for pieces of equipment that emitted this 10 megahertz signal, and they could track the enemy that way, but they didn't have detectors that were good enough to sense them. And so this is what drove Armstrong and Levy to come up with this super heterodyne architecture. They wanted a way to take the 10 megahertz signal, down convert it to something that their detectors could deal with. And so this is what drove a lot of the work on super heterodyne receivers. But that was only 10 megahertz. By World War II, it was up to a couple hundred megahertz. And then today, you know, maybe Dr. Reed, you can tell us, I put down in my notes greater than 100 gigahertz. I guess light's kind of around 300 gigahertz in terms of frequency. So, you know, the whole spectrum now is pretty much usable, and it's occupied. So, you know, we've got huge swaths of spectrum now that everybody's trying to use, not just for military applications, but if you look at automotive radar, there's a lot there at, I guess, 77 gigahertz. And so these are really extremely high frequencies, and they're used everywhere now. So the challenge is we still need to make radios that work at these frequencies. And it turns out that the same technique that Armstrong and Levy came up with, this kind of super heterodyne architecture, this is still very useful today. And indeed, this is one of the techniques that we use in the lab, and I'll talk about this in a few minutes. But I guess one of the things that I wanted to point out is that, when you have a really good concept, a really good idea, it's very durable. And this is a copy of Armstrong's U.S. patent. There's French patents that he and Levy filed over in France. I didn't get that. But this is dated February 8th, 1919. So just over 100 years old. And yet this principle, this concept, is still as valid today as it was 100 years ago. And one of the key takeaways that I hope you take away today is that if you have a really good idea, it's probably going to outlive you. So the things that you guys are studying today, the things that you're doing in terms of your theses and your studies, I would expect a lot of these to have a lot of durability and have a big impact in the future. Maybe not so much today, but ideas build and grow. Another thing is, I was talking with some of the professors before the meeting today, and we were talking about artificial intelligence. And back when we were in school, these were just nascent ideas. We thought they were really cute, but you probably couldn't do much with them. And if I had to guess, I'd probably say at least half of you guys today are involved in artificial intelligence in some way or another, and its application to wireless. So sometimes ideas come before their time, but eventually they get there. And then the other thing is that they may not be on the original technology. You're using some kind of processor today, whether it's a CPU or GPU or something like that. I don't know what's going to be in 10, 15, 20 years. Maybe there's some other kind of processor. But, a really good idea will outlive their creator, and it'll outlive the original technology. The other thing is that good ideas spur other ideas. Sometimes the ideas are better, sometimes not so much. But, you have to go and explore these ideas to find the ones that work and the ones that stick. And that's an important part of it, is to figure out the things that don't work as well as the things that do work. Some of the other things that I learned is that a lot of times even the best of ideas face a lot of headwind. As you develop your theses and you go out into industry, or maybe you even stay in academics, you're always having to promote your idea. You're always having to convince someone. And there's always a lot of people that say, no, that'll never work. And my encouragement to you is, if you believe it, if you've seen the proof, don't give up. Continue to push forward. Try not to take personal the criticism and all that people drive your way, but just believe in your research, believe in what you've done, and continue to push that forward. And eventually, good technology will prevail. And certainly Armstrong, if you look at his background, he had a lot of headwind in his life, and it didn't end well for him, to be quite honest. But that's just a part of life, and sometimes you got to push through all that. But I just want to encourage you, don't give up. If you have great ideas, make sure you see them on through completion. The other thing there is sometimes you find solutions to problems that you didn't know existed. If you have a good idea and you don't know what to do with it, keep it in the back of your mind, because chances are in the next 5 years or 10 years, you probably find a good use for it. So make sure you file your good ideas away and don't lose them, even if they don't look like they have current applicability. So anyway, back to our super hat then versus now. I took kind of Armstrong's patent and drew it out on the top with the tubes, but on the bottom is kind of a more modern interpretation of that, and it's almost element for element very similar. Again, he had a really good idea, and it actually, again, is still in use today. So that's kind of at a detailed schematic level. Here's kind of at a block diagram level, and this is actually what we've got built up in our lab. I know a couple months ago, one of my coworkers came visiting. His name was John Oates. I don't know if he presented this or not. I hope not. Otherwise, it may be a little bit of a review for you. But one of the things that I've been working on the last 5 years is to develop some products around millimeter wave, with the focus being on millimeter wave 5G, so FR2 if you're familiar with the standard there. And FR2, the two bands that are specified today are around 28 gigahertz and 39 gigahertz. There's some others that are being discussed, but I don't think they're in the standard yet. And so what we did here was we had an antenna array, and this particular one shows 16 elements. And what we've got is an analog beamformer that then takes those 16 elements to 16 beamformers, and the function of the beamformer is to align all the phases of those and to put the right gain and phase on them such that they combine coherently on the receive path, and then you do the opposite on the transmit path. But it's just one single element here that then goes to a millimeter, what we call a millimeter wave up-down converter. It's basically just a mixer, just exactly like Armstrong had right here or up there. So we're just converting 28 gigahertz down to our IF frequency, in this case, which is about 4.4 gigahertz. And then we use data converters. We use an ADC to sample that and digitize it. And then on the transmit side, we use a DAC to synthesize the 4.4 gigahertz, and then that gets transmitted. But it's fundamentally the same exact architecture that was used 100 years ago. Nothing's really changed except the operating frequency. So now we're up at 28, and I guess Armstrong and Levy were down around 10 megahertz. So a lot of improvements there, but fundamentally it's exactly the same architecture we had before. Then I guess in terms of what you do with that, I guess over here is where you have your signal processing, and that's what a lot of you guys do in terms of your baseband work. Talking with Dr. Reed and some of the other professors this afternoon about using artificial intelligence, AI, deep learning, to actually do the modulation and demodulation. So that was actually a very interesting discussion there. But back to my job. What my job was to do the architecture for this. So I put together this block diagram and worked with our engineers, and we took that then and we were actually able to build it up, and that's what you see on the left-hand side there. At the time, we only had an 8-element array, so that's an 8-element 28 gigahertz array, and it's kind of hard to see, but behind it we have 8-channel beamformer chip. So those 8 elements go to 8 beamformer channels, and then we go to a down converter, and then the ADC is actually down here on that, so we go across a cable. So this was kind of our first level of prototyping. And then the next thing we did was we said, let's take this and let's take all this electronics in the element and let's integrate it into an array like that. And so I actually did bring one of those today, and I'll float this around. You can take turns looking at it. But this is a 16-channel device. Inside there, of course, we've got this is a 64 version. I'll talk about that in a minute. But inside this device right here, you've got the antenna elements, we've got the beamformer, and the up-down converter is all integrated in that little square. The interface to that is at the 4.4 gigahertz IF. So you can kind of see the stages of how we do our engineering development. We have kind of the hardware development on the bench. We work with that to understand the signal chain, and then we integrate it into sort of a package. Then on the far right over there, that actually is an Ericsson millimeter wave display. I took that picture at Mobile World Congress Americas in September, I think it was. And they didn't use our part. They used one that they developed, I guess, with IBM. And you can go out and search, if you Google IBM Ericsson millimeter wave, something like that, you'll come up with some really good documentation on what's in that little box. But you can kind of see the different phases of development and implementation as we go through the charts there. So one of the things that I've spent a lot of time looking at over the years, my background is mostly with data converters, ADCs in particular, but as we got more and more into wireless, I actually lumped data converters into the category of detectors. And so one of the things that we did here was we plotted out on the horizontal axis the bandwidth of interest, and then on the vertical axis the center frequency of those bandwidths. And so what you see here are FDD, so these are low bands, so up to, I guess typically up to about 2.6 gigahertz, I guess is where the last FDD band is. Down, you kind of see the range of of FDD applications. And then multi-band, you may have a radio that needs to process anywhere from 400 megahertz up to about 1.6 gigahertz of bandwidth. And you'd use this radio to basically capture just that whole spectrum, even though you may not be interested in all of that. And you digitally pick out the bands that you want. So that's kind of what these ovals represent. So that's a TDD application, looking at the RF frequency and then the bandwidth that you may need. And then there's some other applications up there. There's LAA stuff and some new bands. And then there's the millimeter wave IF frequency. And let me jump back a couple slides. So that millimeter wave IF frequency would be the IF frequency that we're using right here. So what we found is that, at least with the technology that's available today, the absolute frequency that you can capture on today's detector seems to max out at around 6 gigahertz. And this is an area that we're working to push higher, and I'm sure our competition is as well. But we want to be able to increase that frequency up towards 12 gigahertz. And certainly there are detectors that will go well above these frequencies, but what we're focused on are high-performance detectors, high-performance receivers, if you will. So the question is, how do we push that forward, and what are the limits of that? And we'll talk about some of that in a minute. But that's really kind of what I've been focusing on over the last couple of years. And really there's two key ways that I see that detectors are being done today. And unfortunately, you don't really see a super het receiver up here for this. You do if you're compounding this and you're using an IF to get down to these frequencies. But basically there's two ways right now. One is direct RF sampling or RF converter. And then the other is what you'd call a zero IF, where you take your RF signal down and you bring it all the way to DC with a sine and cosine and a modulator or demodulator. And so these are kind of the two radio topologies we see for sub 6 gigahertz space right now. And they both have different trade-offs. The RF converter is kind of the most interesting option, and ever since I took my first job 35 years ago, everybody was always asking, when are we going to be able to do RF sampling? When are we going to be able to do RF sampling? And that was 35 years ago, and here we are today, finally, I think, able to achieve that. The challenge there is comparing that to the zero IF architecture. The RF front end is a little bit more complicated for the RF converter. You have to run a little bit extra gain. You have to also do a little bit extra filtering because you don't want to allow in all of the out-of-band signals, otherwise you saturate your receiver. So you've got to filter those down a little bit to prevent your receiver from getting the distortion products added in. But what you get for that is you get a very flexible radio in terms of RF frequencies and bandwidth configurations. The cost for that, though, is it takes a lot of power to run these converters. These may be 4, 5, 6 watts in technology today for 6 gigahertz kind of bandwidth. So they don't come from free, but you do get a lot for the power and the cost that you pay. On the other hand, if you look at a zero IF amplifier, you can get a very simple front end. Matter of fact, in a lot of those radios, you don't even need out-of-band filtering because the architecture of the zero IF filter, it uses sigma delta technology that has its own out-of-band filtering. So in a lot of cases, you don't need the out-of-band filtering. It does require fewer external components, including less external gain. You still need about the same overall gain in the signal chain, but a lot of that gain can be integrated into the radio itself or the ZIF receiver, and it's done at baseband or at DC where it's much easier to do. The trade-off for that, though, is you do get less bandwidth, which is kind of obvious from the comments that I made, but it is at a much lower power. And as a matter of fact, Bluetooth, your cell phone, almost all consumer applications use a zero IF architecture just because they're so power efficient and they can actually be made quite cheaply. So those are the two technologies that we see for sub 6 gigahertz radio space, and a lot of work is being done to push those up. You kind of implied that, or I implied this in this figure, what we want to do is we want to take this all the way up towards 12 gigahertz or so, and that'll allow us to capture a lot of the millimeter wave IF stages at least. And I think if a lot of our customers had their way, we'd go all the way to millimeter wave with the coverage direct. But I don't think that's going to happen for a little while anyway. Oops, wrong direction. So I thought I'd share some more with you. Actually, well, that's okay. I won't pass that around. I did have a blank PCB. This is the picture that I showed of the antenna array. We don't have enough of those little antenna arrays to populate all the boards, so all I got was a blank one, plus the one that's going around. So the other thing I wanted to share with you are some of the products that we're actually doing today. This is one of our transceiver products. This is a 0IF architecture. This particular one happens to be a 2T, 2R configuration, and it's got a lot of other auxiliary functions in there, including an observation receiver and a full DPD. So it's a very highly integrated type platform. The other thing that I want to point out is that whether it's this product or the one that I'll show you in a minute, the products that we have today have a lot more digital content. This one has the DPD, but there's also a lot of calibration loops that are basically digital algorithms that are driving some error to zero. And the requirement for algorithm is growing by leaps and bounds, and I guess historically we've always done just some sort of traditional closed loop application where you're driving some kind of error to zero through classical sense. But one of the things that I think we've talked about some lately is beginning to apply neural networks to that sort of problem, whether it's the DPD loop or whether it's just how to calibrate the chip. These are all things that I think you guys could contribute to in the coming years, is how to take neural networks and deep learning and apply them to analog chip development. And one of the things that we've seen is that as these parts grow, the complexity escalates significantly, and they're very difficult to use. If you were to get this eval board, it's actually a challenge to get it up and operating because of all the things that you have to set in all the registers. So one of the things that I was thinking about is if you could develop some sort of neural network that did all this for you in the background. So, that's kind of a challenge, I guess, to you and to our engineers, is to solve that kind of problem, is how do we make our products easier to use? So I was talking with Zoran yesterday, and he said, you got to talk about our Radioverse. So I put these two slides in at the last minute. So this is what I uploaded last night late, were the next two slides. But what ADI has done is we've taken that radio, so that's the same picture as that, just a different angle. And we've actually put the reference design out on our web. And we've actually developed a portfolio of products that are all related to this. We've got some other products. We've got the ADRV 9009, 9008. There's also an ADRV 9010. These are all variations on the transceiver. The differences being that they have different bandwidths, or they have different digital functionality. Some have DPD, some don't. So a lot of variations depending on what kind of project you might need. But the goal is really to make it simpler for not just industry, but academics to gain access to some of this. So what you'll find out there are a lot of kits, a lot of eval boards. You'll find message boards. You'll find wikis, things like that that you can really go to as a source for getting these designs up and running quickly for your application. So you don't have to worry so much about getting the radio to work as you do about the algorithms and other things that you're doing with it. So I challenge you to go out to analog.com/radioverse, and you can see what's out there. And if you have any questions, you can certainly let me know. I think my email was on the front. Yep, my email is on the front of the presentation. Feel free to contact me, or you can go out here, and there's some contact info there as well. So those are our transceivers. The other one is our RF sampling, and we also have a lot of RF sampling converters there. This particular board has a separate ADC and a DAC. This was an older board. that will work out to the 4.4 gigahertz. That's the board we're using with our millimeter wave transceiver that I showed earlier. But what we've done is we've taken that and the input from the things that we've learned around the millimeter wave and other programs, and we've developed this chip. This is the AD9986, and there's also an AD9988. And these are 4 transmit, 4 receive, or 4 transmit, 2 receive, depending on your application. So lots of applications there. The goal of this part, which this is not released yet, we're just now starting to sample it, is to be able to synthesize or digitize signals out to about 7.5 gigahertz. So a really good direct RF radio platform if that's what you were developing. So what would our customers do with these? I kind of alluded to some of them. I showed you the Ericsson platform earlier. These are massive MIMO platforms. The one on the left is Samsung, and I think this was from an announcement they made at Mobile World Congress this week. As I went out, I grabbed that picture, and that's a 3.5 gigahertz massive MIMO system. The middle one and the one on the right, I took those myself last fall at Mobile World America. The one in the middle is a Nokia 64T64R, and the one on the right is an Ericsson massive MIMO, the same thing. So basically these are all exactly the same radios with some slight variations. I think the Ericsson and Nokia are most similar. I haven't dug into this, but if you notice, Samsung has a slightly different antenna pattern, the way they stagger them. So it'll be interesting to try and figure out what's going on there. But all these radios can be built with either of the architectures I showed earlier, either the direct RF sampling or the zero IF transceiver. Either one works well. We see our customers doing both of those. So next question that I want to talk about is how good or how much bandwidth will we be able to achieve in the future? And this is kind of a popular chart that we like to show. This actually came from Professor Boris Merman out at Stanford University. He actually does a really good job of tracking data converter technology, and he's gone out to ISSCC papers, VLSI papers, and some other sources, and he's kind of created this graph, and he's done it for about the last 10 years. And so you can actually go out and see the progression of technology over the last years. In my career, like I'd said earlier, I've seen bandwidth go from about 10 megahertz up to 6 gigahertz, which is about where we are today. And I guess I put the disclaimer in there for high performance only. But if you do the math on that, that means that the bandwidth's doubled about every 3.8 years. It's not quite Moore's Law, a little bit slower. And I think there's a reason for that. And actually, Dr. Merman talks about it. If you go out, you can watch his video. It's about 20 minutes or so. But he actually talks about this chart. But what he talks about, or one of the points he talks about, is kind of what I've seen. If you look at the horizontal axis on this chart, it's basically Nyquist bandwidth. And then on the vertical axis, it's a Schreier figure of merit, which is the amount of energy it takes to do a conversion per bit, something like that. And what he talks about, I think, is actually very real, and I've seen this myself. Sometimes a manufacturer will choose to push the sample rate higher, so we'll go on this axis for a while, and then we'll say, you know, we're dissipating too much power. We need to do a new design where we're more efficient. And so rather than going this way, we'll go up for a generation, and then a couple years later we'll say, we need a faster part, so we'll go this way. And so I think that's why, if you look at the numbers that I come up with of doubling the speed every 3.8 years versus something more like Moore's Law, where you could say you double every 1.6 years or every 18 months or so, I think that's because what we've done is sometimes we'll go faster, sometimes we'll go more efficient, sometimes we'll go faster, sometimes more efficient. And he kind of has his own explanation of that. The other thing that he points out is that he looked at the last 10 years, and he actually found over the last 10 years that speeds have actually increased 60x in the last 10 years. So what that would mean is if you had a I guess back to my numbers, if you started out at 10 megahertz, that would mean 10 years later you're at 600 megahertz. What he says is that if you look at process advancements alone, it should have been 10x. But he saw a 6x increase, and he accounts for that by saying that designers have figured out better ways to architect their converters to actually improve the bandwidth faster than what the process technology is actually capable of. But again, go out and take a look at his presentation. He's got a pretty good explanation of that. The other thing is he does talk about limits. On the power efficiency limit, he actually says that he believes there is a limit of about 192 dB. If you look at this chart, it shows about 193 dB. He says he thinks that axis is getting compressed. He doesn't think there's a lot more room for improved efficiency, which will impact power dissipation ultimately. But the other good news is he said that he does see no limit in terms of Nyquist bandwidth of these receivers as long as process technologies continue to support faster and faster transistors. So that's a good thing, I guess. But that is directly applicable to the things I think you guys do, and it's applicable to the things I do as well. So we're kind of coming up here on the end. There we go. And I just kind of want to close. I've been really impressed by the things that I discussed with the faculty today, Dr. Reed. And, you know, I think the first time I came, the big thing was software-defined radio. Not too long after that, I heard a lot of talk about cognitive radio. And I don't know the words yet to describe it, but this artificial intelligence kind of radio, I think that's very interesting. And clearly there's a lot of activity going on there. Is there a buzzword that's attached to that, like cognitive and SDR?
Well, I think the more modern buzzword for it is AI-enabled radio.
Okay. All right. So I guess that's kind of what I expect to see over the next couple of years, is a lot of activity in that area. And like I said, I was really glad to hear a lot of the discussion I had with the faculty this morning or this afternoon in regards to that. The other thing is we do have a joke in and around the office. You know, the acronym is ADC and DAC, but what we say is that the D is clearly getting bigger in everything we do. And if you look at our chips, actually I forgot to pass this one around. I'll do it. This is, which one is this? Oh, there it is. This is I think our newest transceiver. This is 809010, ADRF 9010. It's a 4-channel, transmit 4-channel receive with DPD. But if you look at chips like this, if you look at our ADCs and DACs, the analog portion is very tiny. Probably 80% of the chip is digital now, and I see that trend continuing, that in the future the digital content is going to be much higher than where we are even today. So I think that was my last slide. Yep. So thank you for letting me come today and share with you some of the things that I'm doing and some of the thoughts that I have, and I'll be happy to answer any of your questions.
I have a question for you.
Mm-hmm.
Have you guys run into any issues with the Heisenberg uncertainty principle and its application to ADCs?
You're probably asking the wrong person on that, but if I were to speculate, which is probably a bad thing to do, would that apply more to things like noise limitation, the limits of thermal noise and things like that?
Sort of the amount of energy, if you quantize the scale, the amount of energy to go from one quantization level to the next quantization level, given the amount of time, is restricted by physics, by Heisenberg. Just wondering.
Okay, yeah, I can think of some applications. Again, I'm not the right person to ask for that, but listening to our circuit designers talk, I know that there are limitations on the sampling process. We basically do that with a capacitor. So we sample the input network and we do something with that voltage later. And there are fundamental limits on how small we can make that capacitor because of charge quantization.
Yeah.
So
well,
that may be very similar to what you're talking about.
Yeah.
And yeah, that does impact some of the things that we do. where I understand that, it's the size of that capacitor. You have to have fundamentally a capacitor of size X. Otherwise, you start seeing the quantization, which would show up as noise, I think. And because you have a fundamental limit on that capacitor size, that actually impacts the bandwidth of your system. So I think what that would say is that you may have some fundamental limit on the bandwidth of what you could digitize because of that. With that architecture, there may be other architectures that you can use that don't necessarily have a sample capacitor. Again, I'm not the right person, but there are continuous time architectures that don't rely on sample capacitors. So they would probably avoid that particular problem. They may have others, but I think that's probably the best answer you'll get from me along those lines.
Interesting answer. Thank
Yeah.
you.
Anything else? All right, no questions, so I'll have one. I'll give you your quiz for the afternoon. Just kidding. I'm curious, what do you guys do? I mean, my background is mostly radio and data conversion, but I get the sense a lot of what you do is signal processing related. So kind of spout off and tell me kind of what your areas of focus are. I know you're doing something, so quiet's not an answer.
So we're working on the same project right now. It's a cognitive radar, where the radar is supposed to be able to sense the environment and determine where potential interference is and be able to avoid it.
Okay. So is that mostly signal processing kind of area?
It's implementing machine learning algorithms onto a software-defined radar.
Okay. That's interesting.
Remind you want to talk
Sure.
about the paper that I haven't read yet. Tell them about that one.
Okay, so I'm working with a read about MIMO optimization using deep reinforcement learning, and and also I'm working with a read about this what you have mentioned about AI enabled RF how intelligence can be.
Is that for demodulation and modulation purposes?
We're looking at it in a holistic way, like kind of, we're trying to explore what are the key components that AI can help in the RF domain. So we are not focusing on any specific problem. So
Okay.
it's an exploratory.
All right. That sounds very similar to some of the things that I've thought about lately, where you have a very complicated radio and you want to optimize performance.
Right.
You
Right.
use your artificial intelligence then to tweak on your transmitter receiver for best performance in your environment. You know. Okay,
And
good.
also my background is mathematics.
Okay.
He's also looking at the slow evolution and learning of where you point your antenna over the course of the day by learning, just like we were discussing on the
Okay.
earlier today.
Yeah, so one of the projects that I'm working on right now is looking at using MIM switches for beam steering. You know, with the millimeter wave I showed you there, we're actually doing analog beamforming, which is very power hungry. And one of the things that we're looking now is using MIM switches to actually change the phase, or not the phase, the direction of arrival of an array without having to use the analog beamformers. You're using a MIM switch and some sort of delay line or something like that.
So you need to know the DOA variables.
That's right.
You estimated the annual variable.
Yeah, well, we're working with very broad beams, so we're not looking for pencil beams. We're looking for pretty broad angles. And we're looking more right now at maybe time of day shifts in traffic, where during the morning your traffic may be over here, and then in the afternoon it's on this side of the highway.
Oh, this is very similar to the problem that we
The paper that I haven't read yet.
Okay, so I'd be very interested in this paper maybe when you're at a point that it's shareable. But that's one of the problems that I'm working on right now. So maybe we can talk more about that a little bit later. What else? Y'all have really boring class schedules, I can
Don't
tell.
be shy.
I'm working on an analog afterwards well.
Okay. Yeah, and I think that was one of the topics that you had shared with Pete Delos was the analog FFT. Okay. Yeah, we can talk about that later. What else? Somebody on this side of the room's got to speak up.
Yes, this slide we were more application like we look at the land that we have big data, we
Okay.
pattern,
So using machine learning to look at.
blockchain,
Okay. All right. So all you guys kind of stick together. Is that the way this works? Okay. So why do you guys segregate yourself? Y'all need to intermingle a little bit more. You might get some good ideas from each other that way. I'm just kidding, you guys. Anything else?
Yeah, I'm working on the joint communication and control design for autonomous vehicle. So in more particularly for communication systems, more like doing some optimization for the resource allocation to guarantee the communication link between, for example, between autonomous vehicles is below some kind of latency to guarantee the stability of the control system.
Okay. So
it's a kind of joint design.
So does that reside in the network side or in the
Network side.
vehicle?
Network side.
Okay.
More particularly for the network side.
Because you're wanting to optimize or minimize the latency piece.
Yeah, but also have to consider the stability of the control system, and also definitely have to work on the control design for the whole system.
Okay.
It's
Very
a bit
good.
different from the sense you're working.
That's okay. It's still applicable though.
Yeah.
All right. Well, thank you. I appreciate your time this afternoon, and good luck. Thank you.